In this video, we're going to take a very close look at collisions between two molecules. Molecules, or atoms, have electron clouds on the outside. As they approach each other, these electron clouds, which are both negative, tend to repel each other. This repulsive force tends to slow the molecules down, or their kinetic energy decreases. As they get closer, the repulsive force increases. When they get very close, we have a huge repulsive force. That greatly decreases their kinetic energy. This repulsive force can be thought of sort of like a spring. As it goes together, the spring is compressing. It contains stored or potential energy. So like a spring being compressed, the potential energy increases as they go toward each other. More and more and more. If we look at a graph of potential energy versus time, you'll notice when they're far apart, the potential energy is relatively low. As they move closer together, the potential energy increases until it reaches a maximum. So as molecules push against each other, the repulsive force or the potential energy increases, and they slow down, which means their kinetic energy decreases. So we can think of this as kinetic energy is being converted to potential energy. As one goes down, the other one goes up. Kinetic goes down, potential goes up. We can now look at a little graph, and this is a very important graph we're going to be spending some time on. It's called the potential energy diagram. On the y-axis we have potential energy, low and going up, and on this axis we have reaction proceeds. This is sort of like a time axis for the reaction. On the left we have the reactants, and on the right we have the products. Consider this reaction. H2 plus I2 gives 2HI. Remember when we looked at the collision theory, we could consider three different stages to this reaction. The reactants, the activated complex in between, and the products. Remember that the activated complex is a high potential energy, unstable arrangement of atoms from the reactants. It is very short-lived. In this case, its formula is H2I2. Let's look at a potential energy diagram for this reaction. There's the two axes. We start with the reactant molecules H2 and I2. They're quite far apart, they're moving quite fast at this point, so their kinetic energy is high and their potential energy is low. Now they're slightly closer together. Their kinetic is slightly lower and the potential is slightly higher. As they move closer together, their potential goes up and their kinetic goes down. You can see the potential going up by this blue line on the graph. As you get closer and closer together, potential keeps going up. Sooner or later they collide with each other. They have now formed the activated complex, H2I2 in this case. The activated complex has very high potential energy, it's at its highest point here, and the kinetic energy is very low. Remember, the activated complex is a short-lived, unstable species. If the collision was successful, the activated complex will break up into the products, which are two molecules of HI. You notice the HI molecules start moving apart from one another. As they move apart from one another, their potential energy decreases, as you can see by the blue line. As their potential energy decreases, their kinetic energy increases. So as potential keeps going down, kinetic keeps going up. Sooner or later, they form the stabilized products, two molecules of HI. The products have low potential and high kinetic energy. Now we can summarize what happens to potential and kinetic energy during a collision or a reaction. The reactants start out with high kinetic energy and low potential energy. That's why they're fairly low on this graph. As the molecules approach each other, kinetic goes down and it's converted into potential, so the potential energy goes up. When the molecules hit each other, they form a temporary unstable species called the activated complex. The activated complex rearranges to form the product molecules, 2HI in this case. The product molecules move apart and speed up. At this point, potential energy is converted into kinetic, so potential energy goes down. The products at the end of the reaction have low potential energy and high kinetic energy. Let's look at this graph again. The amount of potential energy reactants must gain in order to form the activated complex is called the activation energy, EA. It's indicated by this arrow. You'll notice it's the energy difference between the reactants and the energy of the activated complex. This can be thought of as a barrier to a successful collision. The collision must somehow cross this barrier before it can be successful. If the reactant molecules don't start with sufficient kinetic energy to convert to this much potential energy, the collision will not be successful. Let's look at a case like this. Here we have a collision between H2 and I2 with less kinetic energy than the activation energy. The potential energy that these molecules have is indicated by the red line. Notice as they get closer to each other, their potential goes up. And they collide. But look what happens. They simply bounce off of each other unchanged. And their potential goes down again. Why wasn't this collision successful? It's because they didn't collide with enough kinetic energy to form the activated complex. So what determines this activation energy? Well, it's fixed by the actual nature of the reactants, the numbers and the strengths of bonds in the reactant molecules. For example, the activation energy for this reaction is the energy that it takes for H2 and I2 to collide hard enough to form the activated complex and eventually break these covalent bonds in the H2 and I2 molecules. Activation energy is not affected by the temperature or the concentration of the reactants. It's also not affected by the surface area if it's a solid. It simply has to do with the bonds that are in the molecules. So if the activation energy is not affected by the temperature, what is temperature's role? How does a change in temperature actually change the rate of a reaction? The temperature determines how many or what fraction of the molecules will have kinetic energy greater than or equal to the activation energy, hence make it over that barrier and have a successful collision. In a rather silly way, personifying molecules, we can hopefully understand better how temperature affects the rate of a reaction. Remember the kinetic energy distributions? The number of molecules on this axis, kinetic energy here. This curve, remember, is the distribution at a lower temperature. We have more slow molecules and less fast ones. This curve here represents the distribution at a higher temperature. The activation energy is fixed. So at the lower temperature, the large majority of the molecules indicated by this purple color do not have sufficient kinetic energy for a successful collision. Let's look at these on a potential energy diagram. Let's listen to what they say as they collide with each other. Can we make it over the EA barrier? Let's go. This is harder than I thought. I don't think we can do this. We just don't have the energy to make it any higher. Aw gee, we didn't have a successful collision. No reaction for us. Back to where we started. At this lower temperature, there is a small minority of molecules that do have sufficient kinetic energy for a successful collision. This is indicated by the small number of blue molecules on this graph. So let's look at them on the potential energy graph. There aren't many of us, but I think we can make it over the EA barrier. Let's go. This is going to be so easy. No problem. We got kinetic energy to spare. We're almost there. There we go. We formed the activated complex. We made it over the activation energy barrier, and we're forming the products. But there weren't many of us. I guess we were the few lucky ones. The reaction was slow at this low temperature because only a small fraction of the molecules had sufficient kinetic energy to form the activated complex. Remember all those low energy molecules, the purple ones, that didn't make it over the barrier? The large majority of the molecules did not have sufficient kinetic energy to form the activated complex. That's why the reaction was so slow at this temperature. Now let's see what happens at a higher temperature. Here's the distribution again. Notice at the higher temperature, this whole curve has moved over to the right. The activation energy has stayed the same. So the blue area with molecules greater than or equal to the EA has now got bigger. And at a higher temperature, there is a smaller number of molecules that are too slow. But a larger fraction of the molecules have sufficient kinetic energy to form the activated complex. Let's look at those on the graph. There are more of us at this temperature. We can make it over the EA barrier. Let's go. Again, you can see they have no problem making it over the activation energy barrier. Yeah, a lot more of us have made it over the barrier this time. And more of us are forming products. We've made a lot more product at this temperature. The reaction was faster at high temperature because a larger fraction of the molecules had sufficient energy to form the activated complex. Here's a little question for you. Try it and then turn the video back on and check your answer. The answer is reaction A would be faster. It has a lower activation energy. At the same temperature, the number of molecules with the energy required for a successful collision will be higher in A because the energy requirement is not as high as it is in reaction B. Let's go back to collision geometry. You know that we said that molecules must be aligned properly for a successful collision. Well, even if the collision geometry is not perfect, the reaction can still take place. However, we have to pay a price for that. The activation energy will be a lot higher for a collision with unfavorable geometry. Here is a graph of the two different routes. The lower route is the route for the favorable collision geometry. You notice the EA for this one is quite low, so it's not hard for these molecules to make it over this barrier. But notice the route with the unfavorable collision geometry has a very high activation energy. It's a lot higher with the unfavorable collision geometry. So very few of the molecules with the unfavorable geometry will react.